QuantumMind, written and published by Sonictome. QuantumMind concept merges the principles of quantum physics with the study of consciousness. It proposes that quantum mechanics, the fundamental theory in physics that describes nature at the smallest scales of energy levels, plays a crucial role in the functioning of the human mind. This idea is significant because it challenges traditional views of neuroscience and psychology, offering a revolutionary way to understand mental processes, cognition, and perception. Quantum physics is known for its counterintuitive and complex nature, dealing with phenomena like superposition, where particles can exist in multiple states at once, and entanglement, where particles become interconnected and the state of one instantly influences the state of another, regardless of distance. When these principles are applied to the study of consciousness, they open up new dimensions of thought. Non-locality suggests that consciousness might not be confined to specific areas of the brain, but instead could be a more distributed phenomenon. Superposition implies that thoughts and mental states could exist in multiple potential forms simultaneously until they are observed or focused upon. Entanglement could explain deep connections between individuals, often referred to as mind reading or telepathy from a scientific perspective. Purpose and goals. Understanding the mind from a quantum perspective. The primary goal of exploring the quantum mind is to develop a deeper and more accurate understanding of consciousness and mental processes. By integrating quantum theory with cognitive science, we can potentially unveil the fundamental mechanisms behind thought processes, understand the nature of perception and reality construction, explore the origins and functions of consciousness itself, applications and implications in daily life. Beyond the theoretical insights, the quantum mind concept has practical applications that can significantly impact daily life. These include mental health. New approaches to mental health treatment and understanding of disorders like depression and anxiety, potentially leading to more effective therapies. Personal development. Techniques for enhancing cognitive functions, creativity, and problem-solving skills by harnessing quantum principles. Mindfulness and meditation. Advanced methods for achieving deeper states of mindfulness and meditation, promoting overall well-being. Interpersonal relationships. Insights into the nature of human connections and communication, potentially improving empathy and social interactions. Chapter 1. The Fundamentals of Quantum Physics. Quantum mechanics is the branch of physics that deals with the behavior of particles on the atomic and subatomic scales. Unlike classical physics, which describes macroscopic phenomena and is deterministic, quantum mechanics describes the probabilistic nature of the microscopic world. This theory emerged in the early 20th century and revolutionized our understanding of the universe. At its core, quantum mechanics reveals that particles such as electrons, photons, and atoms do not have definite positions or velocities until they are measured. Instead, they exist in a state of probability, described by a mathematical function known as a wave function. Key principles: superposition, entanglement, and wave-particle duality. Superposition. Superposition is one of the most fundamental principles of quantum mechanics. It states that a particle can exist in multiple states or positions simultaneously until it is observed or measured. For example, an electron in an atom does not orbit the nucleus in a specific path. Rather, it exists in a cloud of probabilities, occupying multiple orbits at once. This concept is famously illustrated by the thought experiment known as Schrödinger's cat, where a cat in a sealed box can be simultaneously alive and dead until the box is opened and its state is observed. Entanglement is another crucial concept in quantum mechanics, where two or more particles become interconnected in such a way that the state of one particle instantly influences the state of the other, regardless of the distance between them. This phenomenon was described by Albert Einstein as spooky action at a distance, because it seems to violate the principle of locality, which states that objects are only directly influenced by their immediate surroundings. Entanglement has been experimentally verified and is a fundamental aspect of quantum theory. It plays a significant role in the development of quantum computing and quantum cryptography. Wave-particle duality. Wave-particle duality is the concept that every particle or quantum entity exhibits both wave-like and particle-like properties. This duality was first demonstrated through experiments such as the double-slit experiment, where particles like electrons or photons create an interference pattern when passed through two slits, indicating wave-like behavior. However, when observed individually, these particles appear to travel through one slit or the other, displaying particle-like characteristics. Wave-particle duality challenges the classical understanding of particles as discrete, point-like objects, and waves as continuous phenomena, showing that quantum entities can exhibit properties of both depending on the experimental setup. Historical background development of quantum theory. The development of quantum theory began in the early 20th century as physicists encountered phenomena that could not be explained by classical physics. Here is a chronological overview of key developments. Max Planck and the quantum hypothesis, 1900. The origins of quantum theory can be traced to Max Planck, who proposed that energy is quantized, meaning it is emitted or absorbed in discrete units called quanta. Planck introduced this idea to explain blackbody radiation, leading to the formulation of Planck's constant, which became a fundamental constant in quantum mechanics. Albert Einstein and the photoelectric effect, 1905. Albert Einstein expanded on Planck's work by explaining the photoelectric effect, where light shining on a metal surface ejects electrons. Einstein proposed that light consists of quanta, later called photons, and that the energy of these photons is proportional to their frequency. This work earned Einstein the Nobel Prize in Physics in 1921 and reinforced the idea of quantization in nature. Niels Bohr and the Bohr model, 1913. Niels Bohr introduced a model of the atom where electrons orbit the nucleus in discrete energy levels. Bohr's model successfully explained the spectral lines of hydrogen and incorporated the idea of quantized energy levels, further advancing the understanding of atomic structure. Louis de Broglie and matter waves, 1924. Louis de Broglie proposed that particles, such as electrons, exhibit wave-like properties. This idea of matter waves was later confirmed by experiments and led to the development of wave mechanics, a central part of quantum theory. Werner Heisenberg and the uncertainty principle, 1927. Werner Heisenberg formulated the uncertainty principle, which states that it is impossible to simultaneously know the exact position and momentum of a particle. This principle highlights the inherent limitations in measuring quantum systems and underscores the probabilistic nature of quantum mechanics. Erwin Schrödinger and the Schrödinger equation, 1926. Erwin Schrödinger developed the wave equation, known as the Schrödinger equation, which describes how the wave function of a quantum system evolves over time. This equation became a cornerstone of quantum mechanics, providing a mathematical framework for understanding the behavior of particles at the quantum level. Paul Dirac and quantum electrodynamics, 1930. Paul Dirac made significant contributions to quantum mechanics by developing quantum electrodynamics, QED, which describes how light and matter interact. Dirac's work led to the prediction of antimatter and advanced the understanding of particle physics. John Bell and Bell's theorem, 1964. John Bell formulated Bell's theorem, which provides a way to test the validity of quantum entanglement. Bell's experiments confirmed the non-local nature of entangled particles, solidifying entanglement as a fundamental aspect of quantum mechanics. Key figures and experiments. Max Planck. Max Planck's introduction of the quantum hypothesis in 1900 marked the beginning of quantum theory. By proposing that energy is quantized, Planck resolved the problem of blackbody radiation and laid the foundation for the development of quantum mechanics. Albert Einstein. Einstein's explanation of the photoelectric effect in 1905 provided strong evidence for the quantization of light. His work on this phenomenon helped establish the particle-like behavior of photons and earned him the Nobel Prize in Physics in 1921. Niels Bohr
Niels Bohr's model of the atom, introduced in 1913, incorporated the idea of quantized energy levels. Bohr's model successfully explained the spectral lines of hydrogen and played a crucial role in the development of atomic physics. Louis de Broglie's hypothesis that particles exhibit wave-like properties was a groundbreaking idea. His concept of matter waves was confirmed by experiments, leading to the development of wave mechanics, and significantly advancing quantum theory.
Werner Heisenberg. Werner Heisenberg's uncertainty principle, formulated in 1927, highlighted the limitations of measuring quantum systems. This principle underscores the probabilistic nature of quantum mechanics and has profound implications for our understanding of the microscopic world. Erwin Schrödinger. Erwin Schrödinger's wave equation, introduced in 1926, provided a mathematical framework for describing the behavior of particles at the quantum level. The Schrödinger equation is a cornerstone of quantum mechanics, essential for understanding the evolution of quantum systems. Paul Dirac. Paul Dirac's work on quantum electrodynamics, QED, advanced the understanding of how light and matter interact. Dirac's contributions to quantum theory led to the prediction of antimatter and had a significant impact on particle physics. John Bell's formulation of Bell's theorem in 1964 provided a way to test the validity of quantum entanglement. Bell's experiments confirmed the non-local nature of entangled particles, solidifying entanglement as a fundamental aspect of quantum mechanics. Double-slit experiment. The double-slit experiment, first performed by Thomas Young in 1801 and later adapted for quantum particles, demonstrates the wave-particle duality of particles like electrons and photons. When particles pass through two slits, they create an interference pattern, indicating wave-like behavior. However, when observed individually, they appear to travel through one slit or the other, displaying particle-like characteristics. Stern-Gerlach experiment. The Stern-Gerlach experiment, conducted by Otto Stern and Walther Gerlach in 1922, demonstrated the quantization of angular momentum. When a beam of silver atoms was passed through a non-uniform magnetic field, it split into discrete components, indicating that angular momentum is quantized. This experiment provided crucial evidence for the quantum nature of particles. Chapter 2. The Nature of Consciousness. Philosophical perspectives. Consciousness, often described as the state of being aware of and able to think about oneself and the environment, has been a central subject in philosophy for centuries. Philosophical inquiry into consciousness dates back to ancient times, with thinkers like Plato and Aristotle exploring the nature of the mind and its relationship to the body. Plato viewed consciousness as a form of recollection, suggesting that knowledge and awareness are innate and accessed through introspection. He believed that the soul existed before birth and would continue after death, with consciousness being a reflection of the soul's knowledge. Aristotle, on the other hand, considered consciousness as an emergent property of the body. He posited that the mind, or soul, and body are intertwined, with the mind being the form of the body, thus emphasizing a more integrated perspective. Descartes' dualism. René Descartes, a pivotal figure in the philosophy of mind, introduced the concept of dualism in the 17th century. He famously asserted, "Cogito, ergo sum," I think, therefore I am, arguing that the mind and body are distinct substances. According to Descartes, the mind is non-physical and capable of thinking, while the body is physical and operates in the material world. This dualistic view has deeply influenced subsequent philosophical and scientific discussions about consciousness. Materialism and physicalism. In contrast to dualism, materialism posits that everything, including consciousness, can be explained in terms of physical processes. Philosophers like Thomas Hobbes and later proponents of physicalism argue that mental states are brain states, and consciousness arises from complex neural activities. This perspective underpins much of contemporary neuroscience and psychology, which seek to understand consciousness through the study of brain functions. Phenomenology. Phenomenologists, such as Edmund Husserl and Maurice Merleau-Ponty, focus on the subjective experience of consciousness. They argue that consciousness is always about something, intentionality, and emphasize the importance of studying first-person experiences. This approach highlights the lived experiences and the ways in which individuals perceive and interact with the world. Scientific approaches. The scientific study of consciousness has progressed significantly, particularly with advancements in neuroscience and cognitive psychology. Researchers employ various methods to investigate the neural correlates and mechanisms underlying conscious experience. Neuroscientific methods techniques such as functional magnetic resonance imaging, fMRI, electroencephalography, EEG, and positron emission tomography, PET, allow scientists to observe brain activity and identify regions associated with different aspects of consciousness, such as perception, attention, and self-awareness. Studies involving patients with brain injuries or disorders provide insights into the neural basis of consciousness. For example, research on split-brain patients has shed light on the role of the corpus callosum in integrating conscious experiences across hemispheres. Cognitive psychology. Cognitive psychologists study consciousness by examining processes like perception, memory, and decision-making. Experimental paradigms, such as the Stroop test or visual masking, help researchers understand how information is processed consciously and unconsciously. The study of altered states of consciousness, including sleep, dreaming, hypnosis, and meditation, also contributes to our understanding of the various dimensions of conscious experience. Quantum theories of consciousness. Some scientists propose that quantum mechanics might play a role in consciousness. The Penrose-Hameroff Orchestrated Objective Reduction, Orch-OR theory, for instance, suggests that quantum processes within neurons could contribute to conscious experience. While controversial and not widely accepted, such theories highlight the potential for interdisciplinary approaches to understanding consciousness. Theories of mind, dualism versus materialism. The debate between dualism and materialism remains central to discussions about the nature of mind and consciousness. Dualism. Dualists, following Descartes, argue that the mind and body are fundamentally different substances. This perspective raises questions about how non-physical mind can interact with the physical body, a problem known as the mind-body interaction problem. Variations of dualism include property dualism, which suggests that mental properties are non-physical attributes of physical substances, and substance dualism, which maintains a strict distinction between mind and body. Materialism. Materialists, or physicalists, contend that all mental phenomena can be explained in terms of physical processes in the brain. They argue that consciousness emerges from the complex interactions of neurons and neural networks. Reductive materialism seeks to explain mental states directly in terms of brain states, while non-reductive materialism allows for mental states to have emergent properties that are not directly reducible to physical processes. Modern theories: integrated information theory and global workspace theory. Integrated information theory, IIT. Developed by Giulio Tononi, integrated information theory posits that consciousness corresponds to the capacity of a system to integrate information. According to IIT, a system is conscious to the extent that it can generate a large amount of integrated information, quantified by a measure called phi-EF. IIT suggests that consciousness is not limited to humans or animals, but can potentially be present in any system capable of integrating information, including artificial systems. This theory provides a framework for understanding the graded nature of consciousness and offers potential explanations for why certain brain structures are associated with conscious experience. Global Workspace Theory, GWT. Proposed by Bernard Bars, global workspace theory likens consciousness to a theater, where a spotlight of attention brings certain information into the global workspace, making it available for various cognitive processes. According to GWT, the brain operates as a collection of specialized processors, and consciousness arises when information is broadcast to the global workspace, allowing for coordinated and flexible responses. This theory emphasizes the role of attention and working memory in conscious experience and aligns with findings from neuroscience regarding the neural correlates of consciousness. Other contemporary theories. Higher-order theories. Higher-order theories suggest that consciousness arises when a mental state is the object of another mental state. For instance, one becomes consciously aware of a thought or perception when it is the subject of a higher-order thought or representation. These theories propose mechanisms for how the brain generates meta-awareness and self-reflective capacities, contributing to the understanding of self-consciousness and introspection. Predictive coding and Bayesian brain hypothesis. The predictive coding framework posits that the brain continuously generates predictions about sensory input and updates these predictions based on incoming information. Conscious perception arises when these predictions are in alignment with the actual sensory input. The Bayesian brain hypothesis extends this idea, suggesting that the brain operates as a Bayesian inference machine, constantly updating its model of the world based on probabilities. This approach provides a unified account of perception, action, and cognition, with implications for understanding the neural basis of consciousness. Chapter 3. Bridging Quantum Physics and Consciousness. QuantumConsciousness Hypotheses. The intersection of quantum physics and consciousness presents a fascinating and controversial field of study. Several hypotheses have been proposed to explain how quantum mechanics might play a role in the workings of the mind. Among these, the Penrose-Hameroff Orch-OR theory and various models of quantum brain dynamics are the most prominent. Penrose-Hameroff Orch-OR theory. The orchestrated objective reduction, ORC-OR theory, developed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, is one of the most well-known quantum consciousness hypotheses. It suggests that consciousness arises from quantum processes occurring within the brain's microtubules. The basis of ORC-OR. Microtubules are cylindrical protein structures that form part of the cytoskeleton within neurons. Penrose and Hameroff propose that these microtubules can function as quantum computers, capable of performing computations that contribute to conscious thought. According to the ORC-OR theory, consciousness results from orchestrated objective reductions, quantum state reductions, occurring within these microtubules. These reductions are orchestrated by biological processes and lead to a collapse of the quantum state, which correlates with moments of conscious awareness. Quantum computation in microtubules. Penrose suggests that classical computation cannot fully explain human consciousness, particularly aspects such as understanding and insight. He argues that quantum computation, with its ability to process vast amounts of information simultaneously, might account for these higher-order cognitive functions. Hameroff adds that microtubules within neurons are ideally suited for quantum processing due to their unique structure and composition. He proposes that tubulin proteins within microtubules can exist in multiple quantum states, and that the coherent superposition of these states enables quantum computations. Objective reduction. Penrose's theory of objective reduction posits that quantum state reduction is not random, but occurs when a certain threshold of gravitational self-energy related to space-time curvature is reached. This process is proposed to be non-computable and fundamental to the nature of consciousness. In the context of the brain, these reductions occur Scientific and philosophical arguments. Critiques of quantum consciousness. Theories decoherence. Problem. One of the primary scientific critiques is the issue of decoherence. Quantum coherence is typically fragile and easily disrupted by interactions with the environment. Critics argue that the warm, wet, and noisy environment of the brain would cause rapid decoherence, making sustained quantum states unlikely. Lack of empirical evidence. Many aspects of quantum consciousness theories remain speculative, with limited direct empirical evidence. Critics emphasize the need for more experimental data to support claims about quantum processes in the brain. Complexity of biological systems. Some scientists argue that the complexity of neural processes can be adequately explained by classical mechanisms without invoking quantum physics. They caution against the tendency to apply quantum mechanics to explain phenomena that are not yet fully understood. Philosophical challenges. Hard problem of consciousness. The philosophical hard problem of consciousness, as articulated by David Chalmers, refers to the difficulty of explaining why and how subjective experiences arise from physical processes. Quantum theories, while offering novel approaches, still face the challenge of bridging the gap between objective neural activities and subjective experiences. Reductionism versus holism. Philosophical debates continue about whether consciousness can be fully explained through reductionist approaches, breaking down complex phenomena into simpler components, or if a holistic perspective is needed. Quantum consciousness theories often straddle this divide, suggesting that quantum processes might provide a bridge between reductionist and holistic views. Empirical evidence and challenges. Despite the critiques, there are ongoing efforts to empirically investigate quantum consciousness hypotheses. Some studies and experimental findings offer tentative support for these ideas, although significant challenges remain. Experimental investigations researchers have conducted experiments to explore quantum coherence in biological systems, such as photosynthetic complexes and avian navigation. These studies suggest that quantum effects can occur in biological contexts, providing a basis for further exploration in the brain. Advances in neuroimaging and molecular biology might enable more precise investigations of quantum processes in neurons. Techniques such as cryo-electron microscopy and single-molecule imaging could provide insights into the structures and dynamics of microtubules and other cellular components. Theoretical developments. Theoretical physicists and neuroscientists are developing models to explore how quantum processes could be maintained in the brain and contribute to cognitive functions. These models often incorporate insights from quantum information theory and complexity science. Researchers are also examining the potential role of quantum entanglement in neural networks and how it might facilitate information integration and synchronization across different brain regions. Challenges and future directions. One of the major challenges in this field is the interdisciplinary nature of the research, requiring collaboration between physicists, neuroscientists, and philosophers. Bridging these disciplines can be difficult, but is essential for advancing our understanding of quantum consciousness. Future research might focus on developing more robust experimental protocols to test quantum hypotheses in the brain. This could involve designing experiments that specifically look for signatures of quantum coherence, entanglement, or tunneling in neural tissues. The exploration of quantum consciousness also has implications for artificial intelligence and quantum computing. Understanding how quantum processes might contribute to consciousness could inform the development of advanced AI systems and enhance our ability to create machines with human-like cognitive capabilities. Chapter 4. The Quantum Brain Neuroscience Meets Quantum Theory. The concept of the quantum brain explores the possibility that quantum mechanics plays a crucial role in the functioning of the brain and the emergence of consciousness. This interdisciplinary field combines insights from neuroscience and quantum physics to investigate how quantum processes might influence neural activities and cognitive functions. Neural networks and quantum processes. Neural networks are the fundamental units of the brain's architecture, consisting of interconnected neurons that transmit information through electrical and chemical signals. Traditional neuroscience has primarily explained neural activities through classical mechanisms, such as action potentials and synaptic transmission. However, recent theories suggest that quantum processes might also be at play. Quantum neurobiology. Quantum neurobiology proposes that quantum effects could be integral to the brain's operations. This idea is based on the notion that the brain's microstructures, such as microtubules, might support quantum phenomena. Microtubules, part of the cytoskeleton within neurons, are involved in maintaining cell shape, intracellular transport, and cell division. Some researchers, like Stuart Hameroff and Roger Penrose, argue that microtubules could act as quantum processors, facilitating quantum computations that contribute to consciousness and cognition. Quantum information processing. The brain's ability to process information efficiently and rapidly could be enhanced by quantum information processing. Quantum computers can perform certain computations much faster than classical computers by leveraging principles like superposition and entanglement. In the context of the brain, quantum information processing might enable the simultaneous exploration of multiple possible solutions to a problem, leading to more efficient decision-making and problem-solving. Quantum entanglement in neural networks. Quantum entanglement, where particles become interconnected and the state of one instantly influences the state of another, might occur within neural networks. Entangled states could facilitate synchronized neural activities across different regions of the brain, contributing to integrated cognitive functions. Entanglement could also enhance the brain's capacity for parallel processing, allowing for the simultaneous processing of diverse information streams and contributing to complex cognitive tasks. Quantum coherence in the brain. Quantum coherence refers to the property of quantum systems to exhibit wave-like behaviors and maintain correlated states over time. The potential for quantum coherence in the brain has significant implications for understanding neural dynamics and cognitive processes. Maintaining quantum coherence. One of the major challenges in exploring quantum coherence in the brain is the issue of decoherence. Quantum coherence is typically fragile and easily disrupted by interactions with the environment. However, some researchers propose that certain biological structures might protect quantum coherence, even in the brain's warm and noisy environment. Studies on photosynthetic complexes and avian navigation systems suggest that quantum coherence can be maintained in biological systems. If similar mechanisms exist in the brain, they could play a role in maintaining coherent quantum states within neurons. Quantum coherence and consciousness. Quantum coherence might be essential for the integration of information across different regions of the brain, leading to unified conscious experiences. Coherent quantum states could enable the brain to synchronize activities and create a holistic perception of the environment. The role of quantum coherence in consciousness remains speculative, but ongoing research aims to identify potential mechanisms and empirical evidence supporting this idea. Implications for cognitive processes. If quantum processes are indeed at play in the brain, they could have profound implications for various cognitive functions, including memory, perception, decision-making, creativity, and problem-solving. Memory, perception, and decision-making. Quantum memory formation and retrieval might involve quantum processes that enhance the brain's capacity for information storage and access. Quantum coherence could facilitate the encoding of information in a more efficient and interconnected manner, leading to more robust and flexible memory systems. Quantum superposition could allow for the simultaneous representation of multiple memory states, enabling the brain to quickly retrieve relevant information and make associations between different memories. Quantum perception.
The process of interpreting sensory information to create a coherent view of the world might benefit from quantum processing. Quantum entanglement and coherence could enhance the brain's ability to integrate sensory inputs from different localities, leading to more accurate and holistic perceptions. Quantum tunneling might play a role in synaptic transmission, influencing how sensory information is processed at the synaptic level, and contributing to developing an efficient perception of stimuli. Quantum decision-making. Decision-making involves evaluating multiple options and selecting the most appropriate course of action. Quantum processes could enhance decision-making by allowing the brain to simultaneously explore multiple possibilities and weigh their potential outcomes.
Quantum superposition might enable the brain to consider various scenarios in parallel, leading to faster and more informed decisions. Quantum entanglement could also facilitate the integration of information from different neural networks, contributing to more coherent and holistic decision-making processes. Creativity and problem-solving. Quantum creativity. Creativity, the ability to generate novel ideas and solutions, could be influenced by quantum processes. Quantum superposition allows for the simultaneous exploration of multiple creative possibilities, enhancing the brain's capacity for innovative thinking. Quantum coherence might enable the brain to integrate diverse information streams and make unconventional connections between seemingly unrelated ideas, leading to more original and creative solutions. Quantum problem-solving. Problem-solving involves identifying solutions to complex challenges. Quantum processes could enhance problem-solving by allowing the brain to explore multiple solution pathways simultaneously and identify the most effective approach. Quantum entanglement and coherence could facilitate the integration of information from different cognitive domains, leading to more comprehensive and effective problem-solving strategies. Empirical evidence and challenges. While the theoretical implications of quantum processes in the brain are intriguing, empirical evidence remains limited, and significant challenges need to be addressed. Experimental investigations. Experimental studies aim to identify quantum effects in the brain and their potential contributions to cognitive functions. Techniques such as functional magnetic resonance imaging, fMRI, electroencephalography, EEG, and positron emission tomography, PET, are used to study neural activities and their potential quantum correlations. Researchers also explore the properties of microtubules and other cellular structures to determine if they can support quantum coherence and information processing. Challenges and future directions. One of the main challenges is the difficulty of maintaining quantum coherence in the brain's warm and noisy environment. Researchers are investigating potential mechanisms that might protect quantum states within neural tissues. Another challenge is the need for interdisciplinary collaboration between physicists, neuroscientists, and cognitive scientists. Bridging these fields is essential for developing comprehensive models and experimental protocols to study quantum brain dynamics. Future research might focus on developing new techniques to detect and measure quantum effects in the brain, as well as designing experiments that specifically test the predictions of quantum consciousness theories. Chapter 5. Quantum Mind and Reality. Perception and reality. The relationship between perception and reality has long been a subject of philosophical inquiry. In the realm of quantum mechanics, this relationship takes on a new dimension, emphasizing the role of the observer and the profound ways consciousness might shape the nature of reality itself. The role of the observer in quantum mechanics. One of the most intriguing aspects of quantum mechanics is the role of the observer. Unlike classical physics, where measurements are passive and merely reveal pre-existing properties, quantum mechanics suggests that the act of observation itself can influence the state of a system. This phenomenon is exemplified in several key principles and experiments. Wave-particle duality. Particles such as electrons and photons exhibit both wave-like and particle-like properties. Which property they display depends on the type of measurement being performed. This duality is strikingly demonstrated in the famous double-slit experiment. When particles pass through two slits and are not observed, they create an interference pattern typical of waves. However, if an observer measures which slit a particle goes through, the interference pattern disappears and the particles behave like classical particles. This suggests that the act of measurement collapses the wave function, a mathematical representation of all possible states of a system, into a single outcome. The Heisenberg uncertainty principle. Formulated by Werner Heisenberg, this principle states that it is impossible to simultaneously know both the exact position and momentum of a particle. The more precisely one of these properties is measured, the less precisely the other can be known. This intrinsic uncertainty is not due to limitations in measurement technology, but is a fundamental property of nature. The uncertainty principle underscores the role of the observer in defining certain aspects of reality, as the very act of observation imposes limits on what can be known about a system. Schrödinger's cat paradox. Erwin Schrödinger's thought experiment involving a cat that is simultaneously alive and dead until observed highlights the strange implications of quantum mechanics for reality. The cat's fate is entangled with a quantum event, and it remains in a superposition of states until an observer checks the outcome. This paradox illustrates how observation can determine the state of a macroscopic system based on a quantum event. How consciousness shapes reality. The implications of quantum mechanics suggest that consciousness may play a fundamental role in shaping reality. This perspective challenges traditional views of an objective, observer-independent universe and raises profound questions about the nature of existence. Quantum measurement problem. The quantum measurement problem revolves around understanding how and why the collapse of the wave function occurs. Some interpretations, like the Copenhagen interpretation, posit that observation by a conscious observer causes the collapse, bringing a definite outcome into existence. This idea suggests a direct link between consciousness and the physical world, implying that our perceptions and choices might influence the fabric of reality itself. Participatory anthropic principle. Proposed by physicist John Archibald Wheeler, the participatory anthropic principle suggests that the universe requires observers to bring it into existence. According to this view, the act of observation is fundamental to the creation of reality, and the universe becomes real through the conscious experiences of observers. Wheeler's principle aligns with certain philosophical perspectives that emphasize the interdependence of mind and reality, where consciousness is not merely a passive observer, but an active participant in the unfolding of the universe. Implications for conscious experience. If consciousness shapes reality, it raises profound questions about the nature of human experience and the potential for individuals to influence their own reality. This perspective has implications for fields such as psychology, where the power of belief and perception can impact mental health and well-being. It also suggests a deeper interconnectedness between individuals and the cosmos, where each conscious being contributes to the collective reality. Quantum cognition. Quantum cognition is an emerging field that applies principles of quantum mechanics to understand cognitive processes. This approach offers novel insights into decision-making, probability, and the workings of the mind. Decision-making and probability. Traditional cognitive models often rely on classical probability theory to explain decision-making and reasoning. However, quantum cognition introduces the idea that cognitive processes might be better understood through the lens of quantum probability. Quantum probability. Quantum probability differs from classical probability in that it allows for superposition and entanglement. In classical probability, outcomes are mutually exclusive and additive, while in quantum probability, outcomes can exist in a superposition and interfere with each other. This framework can better capture the complexity and ambiguity of human decision-making. For example, individuals often hold contradictory beliefs or make decisions that appear irrational from a classical perspective. Quantum probability accommodates these phenomena by allowing for the coexistence of multiple potential outcomes until a decision is made. Contextuality in decision-making. Quantum cognition emphasizes the importance of context in decision-making. Just as the outcome of a quantum measurement can depend on the experimental setup, human decisions can be influenced by the context in which choices are presented. Experiments in cognitive psychology, such as the framing effect, demonstrate how the same decision can yield different outcomes depending on how options are framed. Quantum models provide a mathematical basis for understanding these context-dependent effects. Quantum superposition and decision states. In quantum cognition, decisions are modeled as superpositions of potential outcomes. An individual in a state of indecision can be thought of as being in a superposition of different decision states. When a choice is made, this superposition collapses into a single outcome, analogous to the collapse of the wave function in quantum mechanics. This approach offers a dynamic and flexible model for understanding the fluid nature of human thought and decision-making processes. The quantum approach to cognitive science. Quantum cognitive models are reshaping our understanding of various cognitive phenomena, offering fresh perspectives on classical problems in psychology and neuroscience. Quantum models of memory. Traditional models of memory often treated as a static storage system. Quantum models, however, propose that memory operates in a more dynamic and interconnected manner, with quantum entanglement playing a role in the association and retrieval of information. This perspective can explain phenomena such as the rapid formation of associations and the retrieval of contextually relevant memories, which classical models struggle to account for. Perception and quantum interference. Quantum cognitive models suggest that perception might involve quantum interference, where multiple potential perceptual states interfere and combine to produce a coherent experience. This can help explain perceptual ambiguities and the brain's ability to resolve conflicting sensory information. The concept of quantum interference in perception aligns with findings from neuroscience, showing that the brain integrates information from different sensory modalities to create a unified perceptual experience. Quantum decision theory. Quantum decision theory applies quantum principles to understand complex decision-making processes. It provides a framework for modeling the probabilistic nature of human choices and the influence of context and prior experiences. This approach can enhance our understanding of decision-making in uncertain and ambiguous situations, offering more accurate predictions of human behavior compared to classical models. Chapter 6. Practical Applications. Quantum Techniques for Mental Enhancement. The convergence of quantum theory and consciousness has given rise to various techniques aimed at enhancing mental performance and overall well-being. By integrating principles of quantum mechanics with practices like meditation, mindfulness, visualization, and intention setting, individuals can potentially harness the power of the mind in profound ways. Meditation and mindfulness. Meditation and mindfulness practices have long been recognized for their benefits to mental and physical health. When viewed through the lens of quantum theory, these practices may also facilitate quantum coherence and synchronization within the brain, enhancing cognitive function and emotional regulation. Quantum coherence and meditation, particularly practices that promote deep focus and relaxation, can help synchronize neural activities, leading to increased coherence across different brain regions. This coherence might mirror quantum coherence, where different parts of a quantum system maintain correlated states. Enhanced neural coherence can improve cognitive functions such as attention, memory, and creativity. Studies have shown that regular meditation leads to structural changes in the brain, such as increased gray matter density in regions associated with learning, memory, and emotional regulation. Mindfulness and observational awareness. Mindfulness involves maintaining a non-judgmental awareness of the present moment, which can be likened to the observer effect in quantum mechanics. By cultivating a mindful presence, individuals can become more attuned to their thoughts and emotions, influencing their mental state in positive ways. Practicing mindfulness can lead to a greater sense of clarity and calm, reducing stress and anxiety. It also promotes neuroplasticity, the brain's ability to reorganize itself by forming new neural connections, which can enhance overall mental resilience and adaptability. Meditation techniques for quantum mind enhancement. Various meditation techniques, such as transcendental meditation, focused attention meditation, and open monitoring meditation, can be tailored to harness the benefits of quantum coherence and mindfulness. Techniques that incorporate visualization and intention setting can amplify the effects of meditation, aligning the mind with desired outcomes and promoting a sense of purpose and direction. Visualization and intention setting. Visualization and intention setting are powerful techniques that can influence the subconscious mind and potentially interact with quantum processes to manifest desired outcomes. These practices involve creating vivid mental images and setting clear intentions, which can align one's mental state with specific goals. The power of visualization. Visualization involves mentally rehearsing a desired outcome, creating detailed and vivid images of achieving specific goals. This practice can stimulate the same neural pathways involved in actual performance, enhancing the likelihood of success. Athletes, performers, and high achievers often use visualization to improve their performance. By repeatedly visualizing success, individuals can build confidence, reduce anxiety, and enhance their focus and motivation. Intention, setting, and quantum mechanics. Intention setting involves clearly defining and focusing on specific goals or outcomes. From a quantum perspective, setting an intention can be seen as influencing the probability of certain outcomes, aligning the mind with the desired reality. Research in fields like positive psychology and neuroscience supports the effectiveness of intention setting. Clear intentions can activate the brain's reward system, increase motivation, and enhance goal-directed behavior. Practical techniques for visualization and intention setting. Guided imagery. Using guided imagery recordings or scripts can help individuals create detailed mental images and reinforce positive intentions. These recordings often combine relaxation techniques with vivid visualizations to enhance the effectiveness of the practice. Vision boards. Creating a vision board with images and words representing desired goals can serve as a tangible reminder of intentions. Regularly visualizing the board can reinforce positive beliefs and motivate action toward achieving those goals. Affirmations. Repeating positive affirmations related to specific intentions can rewire the subconscious mind, promoting a mindset conducive to achieving those goals. Combining affirmations with visualization can amplify their impact. Quantum healing. The concept of quantum healing explores the mind-body connection and the potential for quantum processes to influence physical health. This approach integrates traditional healing practices with insights from quantum mechanics, offering alternative therapies that harness the power of the mind to promote healing and well-being. Mind-body connection. The mind-body connection refers to the intricate relationship between mental and physical health. Quantum healing emphasizes the role of consciousness and intention in influencing the body's healing processes. Psychoneuroimmunology. Psychoneuroimmunology, PNI, studies the interaction between psychological processes, the nervous system, and the immune system. Research in PNI has shown that stress, emotions, and thoughts can significantly impact immune function and overall health. Practices that promote positive mental states, such as meditation, mindfulness, and visualization, can enhance immune function, reduce inflammation, and improve overall health. These effects are thought to be mediated by the brain's influence on hormonal and immune responses. Placebo effect. The placebo effect is a well-documented phenomenon where patients experience real improvements in their condition after receiving a treatment with no therapeutic value. This effect underscores the power of belief and expectation in the healing process. Quantum healing suggests that the mind's belief in a treatment's efficacy can influence the body's healing mechanisms, aligning with the concept that consciousness can shape physical reality. Epigenetics. Epigenetics studies how environmental factors and behaviors can influence gene expression. Positive mental states and healthy behaviors can lead to beneficial epigenetic changes, promoting health and longevity. Practices like mindfulness, meditation, and intention setting can potentially induce positive epigenetic modifications, enhancing resilience and reducing the risk of chronic diseases. Alternative therapies and quantum medicine. Quantum medicine encompasses various alternative therapies that integrate quantum principles to promote healing and well-being. These therapies often emphasize the role of consciousness, energy, and intention in the healing process. Energy healing practices such as Reiki, Qigong, and therapeutic touch focus on manipulating the body's energy fields to promote healing. Practitioners believe that energy imbalances or blockages can lead to illness, and that restoring the body's natural energy flow can enhance health. While the mechanisms of energy healing are not fully understood, some theories suggest that these practices might influence quantum fields and processes within the body, promoting coherence and balance at a fundamental level. Quantum biofeedback. Quantum biofeedback involves using devices that measure physiological signals, such as heart rate variability, skin conductance, and brainwave activity, to provide feedback and promote self-regulation. These devices aim to enhance awareness and control over physiological states, promoting relaxation and healing. By providing real-time feedback, quantum biofeedback can help individuals develop skills to manage stress, improve focus, and enhance overall well-being. This approach aligns with the principles of quantum coherence and synchronization, promoting harmony within the body's systems. Holistic and integrative medicine. Holistic and integrative medicine approaches treat the whole person, addressing physical, mental, emotional, and spiritual aspects of health. These approaches often incorporate quantum principles, recognizing the interconnectedness of mind and body. Integrative therapies, such as acupuncture, herbal medicine, and mind-body practices, aim to restore balance and promote healing through natural and non-invasive means. These therapies emphasize the role of consciousness and intention in the healing process. Case studies and empirical evidence. While quantum healing remains a controversial and largely speculative field, several case studies and empirical investigations provide insights into its potential benefits. Case studies. Numerous anecdotal reports and case studies suggest that individuals have experienced significant improvements in their health and well-being through practices like meditation, visualization, and energy healing. These accounts highlight the potential for mind-body techniques to influence health outcomes. For example, some cancer patients report experiencing remission or improved quality of life after incorporating mind-body practices into their treatment regimen. While these cases do not constitute scientific proof, they suggest avenues for further investigation. Empirical investigations. Scientific studies have explored the effects of meditation, mindfulness, and other mind-body practices on health outcomes. Research has demonstrated that these practices can reduce stress, lower blood pressure, enhance immune function, and improve mental health. Studies on the placebo effect also provide empirical support for the power of belief and intention in healing. Research in psychoneuroimmunology and epigenetics further elucidates the mechanisms by which mental states can influence physical health. Chapter 7. Ethical and philosophical considerations. Ethical implications. As quantum mind theories gain traction, they raise profound ethical questions and considerations. These theories challenge conventional understandings of free will, responsibility, and morality, prompting a re-evaluation of fundamental ethical principles. The impact of quantum mind. Theories on free will. Quantum mind theories suggest that consciousness and quantum mechanics are deeply intertwined, leading to a re-examination of the concept of free will. If the mind operates at a quantum level, where outcomes are probabilistic and influenced by observation, the deterministic view of free will may need to be reconsidered. Probabilistic nature of decisions. In classical physics, the universe operates in a deterministic manner, where all events are determined by prior states. However, quantum mechanics introduces indeterminacy, where certain events cannot be predicted with certainty and are instead described by probabilities. If the brain functions at a quantum level, decisions may also follow probabilistic patterns rather than deterministic ones. This suggests that free will might involve choosing among a range of possible outcomes rather than following a predetermined path. This shift challenges the traditional view of free will as completely autonomous and uninfluenced by external factors. The role of consciousness in decision-making. Quantum mind theories propose that consciousness plays an active role in collapsing quantum states into definite outcomes. This implies that conscious choices influence reality at a fundamental level. The notion that consciousness can affect physical states introduces a new dimension to free will, where the mind actively participates in shaping reality. This perspective emphasizes the importance of awareness and intention in decision-making, potentially enhancing the sense of agency and responsibility. Responsibility and morality. The ethical implications of quantum mind theories extend to concepts of responsibility and morality. If consciousness and free will operate within a quantum framework, traditional notions of moral responsibility may need to be reinterpreted. Moral responsibility in a quantum context. In a deterministic universe, moral responsibility is often linked to the ability to make free choices. If quantum mechanics introduces indeterminacy, the concept of moral responsibility becomes more complex. Quantum mind theories suggest that individuals have a degree of influence over outcomes through conscious choices. This reinforces the idea that individuals are morally responsible for their actions, as their intentions and awareness play a crucial role in shaping reality. Ethical implications of interconnectedness. Quantum mechanics highlights the interconnectedness of all things, where particles can be entangled and influence each other across vast distances. This interconnectedness extends to human consciousness, suggesting that individuals are not isolated entities but part of a larger, interdependent system. Recognizing the interconnected nature of consciousness and reality has profound ethical implications. It emphasizes the importance of compassion, empathy, and cooperation, as actions can have far-reaching consequences beyond the immediate context. This perspective aligns with ethical principles that prioritize collective well-being and the greater good. Philosophical reflections. Quantum mind theories also invite deep philosophical reflections on the nature of self and identity, as well as the interconnectedness of all things. These reflections challenge traditional philosophical paradigms and offer new insights into the human experience. The nature of self and identity. Quantum mind theories prompt a re-evaluation of the nature of self and identity. If consciousness operates at a quantum level, it raises questions about the boundaries and continuity of the self. Quantum self-traditional views of the self often emphasize a fixed and continuous identity. However, quantum mind theories suggest that the self might be more fluid and dynamic, influenced by quantum processes. The concept of a quantum self implies that identity is not static, but constantly evolving, shaped by conscious experiences and choices. This perspective aligns with philosophical views that emphasize the malleability of the self and the role of consciousness in self-formation. Non-locality and the self-quantum mechanics introduces the idea of non-locality, where particles can be entangled and influence each other instantaneously across distances. This principle challenges the notion of a localized individual self, suggesting that consciousness might also be non-local and interconnected. The idea of a non-local self resonates with spiritual and philosophical traditions that emphasize the unity of all beings and the interconnectedness of consciousness. It suggests that individual identity is part of a larger, universal consciousness, blurring the boundaries between self and other. The interconnectedness of all things. Quantum mechanics reveals a deeply interconnected universe, where particles and events are entangled and interdependent. This interconnectedness extends to human consciousness, offering profound philosophical insights into the nature of reality. Entanglement and human relationships. The principle of entanglement suggests that particles remain connected and influence each other regardless of distance. This concept can be applied to human relationships, where individuals are interconnected through shared experiences and emotions. Understanding human relationships through the lens of entanglement emphasizes the importance of empathy, compassion, and mutual support. It suggests that actions and emotions resonate beyond individual boundaries, impacting the collective consciousness. Holistic perspective on reality. Quantum mechanics challenges the reductionist view of reality, which breaks down the universe into isolated components. Instead, it promotes a holistic perspective, where everything is interconnected and interdependent. Adopting a holistic view of reality encourages a sense of unity and interconnectedness with the universe. It aligns with philosophical traditions that emphasize harmony with nature and the interconnectedness of all life forms. This perspective fosters a deeper appreciation for the complexity and beauty of the cosmos. Philosophical implications for human existence. The philosophical implications of quantum mind theories extend to questions about the nature of human existence and the purpose of life. Existential reflections. Quantum mind theories invite existential reflections on the nature of reality and the role of consciousness in shaping existence. They challenge deterministic and materialistic views, suggesting that consciousness plays an active and participatory role in the universe. This perspective encourages individuals to explore their purpose and meaning in life, recognizing the potential for consciousness to influence reality and create meaningful experiences. Spiritual and metaphysical insights. Quantum mind theories resonate with spiritual and metaphysical perspectives that emphasize the unity of consciousness and the interconnectedness of all things. They offer insights into the nature of existence that go beyond materialistic and reductionist paradigms. Integrating quantum mind theories with spiritual and metaphysical traditions can lead to a deeper understanding of the self and the universe, promoting a sense of wonder and reverence for the mysteries of existence. Chapter 8. Future directions and research. Current research trends. As the fields of quantum physics and neuroscience continue to intersect, research into quantum consciousness is gaining momentum. Ongoing studies and technological advancements are paving the way for a deeper understanding of the quantum mind. Ongoing studies in quantum consciousness. Current research in quantum consciousness is diverse and multidisciplinary, drawing from quantum physics, neuroscience, cognitive science, and philosophy. These studies aim to unravel the complex relationship between quantum mechanics and conscious experience. Penrose-Hameroff Orch-OR theory. The Penrose-Hameroff orchestrated objective reduction, Orch-OR theory, posits that consciousness arises from quantum processes within microtubules in brain neurons. Ongoing research is exploring the feasibility of this theory, examining the role of microtubules in neural function and their potential to support quantum coherence. Experiments are being conducted to detect quantum states within microtubules and understand how these states could influence neural activity. Advances in imaging and spectroscopy techniques are crucial in this endeavor, allowing researchers to observe and measure quantum phenomena in biological systems. Quantum brain dynamics. Research in quantum brain dynamics investigates how quantum processes might underlie cognitive functions such as perception, memory, and decision-making. This includes studies on quantum coherence and entanglement in neural networks and their potential impact on information processing in the brain. Computational models are being developed to simulate quantum effects in neural systems, providing insights into how these effects could contribute to complex cognitive functions. These models aim to bridge the gap between quantum mechanics and brain dynamics, offering a framework for understanding the quantum mind. Quantum cognition. Quantum cognition is an emerging field that applies principles of quantum mechanics to model cognitive processes. Researchers are exploring how quantum probability theory can explain decision-making, problem-solving, and other cognitive phenomena that classical models struggle to account for, Studies in quantum cognition investigate how concepts like superposition and entanglement can be applied to mental states and cognitive processes. This research is expanding our understanding of how the brain handles uncertainty, ambiguity, and complex information. Technological advancements. Technological advancements are critical in advancing research in quantum consciousness. New tools and techniques are enabling more precise and sophisticated investigations into the quantum aspects of the mind. Advanced imaging techniques. Advances in imaging technologies such as quantum-enhanced MRI and quantum sensors are providing unprecedented insights into the brain's quantum processes. These techniques allow researchers to observe and measure quantum states in biological systems with high precision. Quantum-enhanced imaging techniques are being used to study neural coherence and entanglement, shedding light on the potential quantum underpinnings of consciousness. These advancements are crucial for validating theories like Orch-OR and understanding the role of quantum mechanics in the brain. Quantum computing. Quantum computing is revolutionizing the field of computational neuroscience by providing new ways to model and simulate complex neural processes. Quantum computers can perform computations that classical computers cannot, allowing researchers to explore quantum effects in neural networks more effectively. Quantum algorithms are being developed to simulate brain dynamics and cognitive processes, offering new insights into how quantum mechanics might influence consciousness. These simulations can help validate theoretical models and guide future experimental research. Neurotechnology. Neurotechnology, including brain-computer interfaces, BCIs, and neural implants, is being used to study the brain's quantum processes and their relationship to consciousness. These technologies enable direct interaction with neural systems, allowing researchers to manipulate and measure quantum states in real time. BCIs and neural implants are being integrated with quantum sensors and imaging techniques to investigate the brain's quantum coherence and entanglement. This multidisciplinary approach is providing new ways to explore the quantum mind and its implications for cognitive function. Future prospects. The future of quantum mind studies holds exciting potential for breakthroughs in understanding consciousness and its relationship to the quantum realm. As research progresses, several key areas are poised for significant advancement. Potential breakthroughs. Empirical validation of quantum consciousness. Theories. One of the most critical future prospects is the empirical validation of theories like Orch-OR and quantum brain dynamics. Advances in imaging, spectroscopy, and computational modeling are expected to provide more robust evidence for quantum processes in the brain. Breakthroughs in detecting and measuring quantum states in neural systems could revolutionize our understanding of consciousness. These discoveries would confirm the role of quantum mechanics in cognitive function and provide a solid foundation for further research. Integration of quantum mechanics and neuroscience. Future research is likely to see greater integration between quantum mechanics and neuroscience, leading to new interdisciplinary fields and research programs. This integration will foster collaborations between physicists, neuroscientists, and cognitive scientists, driving innovations in both theory and practice. The development of comprehensive models that incorporate both quantum and classical aspects of brain function will be a significant milestone. These models will help explain the interplay between quantum processes and neural dynamics, offering a unified framework for understanding consciousness. Quantum mind applications in artificial intelligence insights from QuantumMind research could have profound implications for artificial intelligence, AI. Understanding how quantum processes contribute to human cognition could inspire the development of quantum-based AI systems that mimic human thought processes more accurately. Quantum computing and quantum algorithms could enhance the capabilities of AI, enabling more efficient and sophisticated information processing. These advancements could lead to AI systems with improved problem-solving, decision-making, and learning abilities, transforming various fields and industries. The future of quantum mind studies. Expanding research horizons. The future of quantum mind studies will likely involve exploring new research horizons, including the investigation of consciousness in non-human systems and the study of quantum effects in other biological processes. Researchers may also explore the implications of quantum mind theories for understanding altered states of consciousness, such as those induced by meditation, psychedelics, or near-death experiences. These studies could provide deeper insights into the nature of consciousness and its relationship to the quantum realm. Ethical and societal implications. As quantum mind research advances, it will be essential to consider the ethical and societal implications of these discoveries. Understanding the quantum nature of consciousness could have far-reaching effects on philosophy, psychology, and our understanding of the self. Ethical considerations will be crucial in applying quantum mind research to technologies like BCIs and AI. Ensuring that these advancements are used responsibly and ethically will be a key challenge for future researchers and policymakers. Educational and public awareness. Increasing public awareness and education about quantum mind theories and their implications will be important for fostering informed discussions and decision-making. Promoting interdisciplinary education that combines quantum mechanics, neuroscience, and cognitive science will help cultivate the next generation of researchers and thinkers. Public engagement initiatives such as science communication programs and interactive exhibits can help demystify quantum mind concepts and highlight their relevance to everyday life. These efforts will contribute to a broader understanding and appreciation of the profound connections between consciousness and the quantum world. Conclusion. As we draw to a close, it's essential to reflect on the major themes and insights covered in our exploration of the quantum mind. This journey through quantum physics, consciousness, and their intersection reveals profound implications for our understanding of reality and ourselves. Summary of key points. 1. Quantum mechanics and consciousness. The exploration of quantum mechanics and its potential relationship with consciousness has unveiled a tapestry of intriguing concepts. Quantum mechanics introduces principles such as superposition, entanglement, and wave-particle duality, which challenge classical views of determinism and linear causality. These principles suggest a universe where particles and events are interconnected in ways that transcend classical boundaries, opening the door to new understandings of consciousness. Quantum consciousness theories, such as the Penrose-Hameroff Orch-OR theory and quantum brain dynamics, propose that consciousness might arise from quantum processes within the brain. These theories suggest that the mind operates not only through classical neural mechanisms, but also through quantum coherence and entanglement. While empirical validation is still evolving, these ideas offer a novel perspective on how consciousness might function at a fundamental level. 2. The nature of consciousness. Defining consciousness has been a central theme in this exploration. Philosophical perspectives and scientific approaches have offered varying definitions, from dualistic views that separate mind and body to materialistic views that seek to explain consciousness solely through neural processes. Modern theories such as integrated information theory and global workspace theory provide frameworks for understanding consciousness as a complex, emergent property of neural activity and information integration. Quantum mind theories add a new dimension to this discussion, suggesting that consciousness might involve quantum processes that interact with neural activity. This integration of quantum and classical perspectives challenges traditional notions of self and identity, emphasizing a more fluid and interconnected view of consciousness. 3. Bridging quantum physics and consciousness. The attempt to bridge quantum physics and consciousness has led to fascinating hypotheses and debates. The Penrose-Hameroff Orch-OR theory and quantum brain dynamics offer potential mechanisms for how quantum processes could influence cognitive functions and conscious experience. While these theories face critiques and challenges, they stimulate important discussions about the nature of consciousness and the limits of scientific inquiry. 4. The quantum brain. The study of the quantum brain explores how neural networks might exhibit quantum coherence and entanglement. Technological advancements in imaging and computational modeling are enabling researchers to investigate these possibilities, shedding light on how quantum processes could impact memory, perception, and decision-making. The potential implications for cognitive processes and mental enhancement are profound, suggesting that our understanding of the brain might be fundamentally altered by quantum insights. 5. Quantum mind and reality. The intersection of quantum mind theories with our understanding of reality highlights the role of the observer and consciousness in shaping the world. The observer effect in quantum mechanics suggests that consciousness might influence physical reality, leading to new perspectives on decision-making, probability, and cognitive science. These insights challenge traditional views of reality and invite deeper reflections on how our mental states interact with the world. 6. Practical applications. Quantum techniques for mental enhancement, such as meditation, mindfulness, visualization, and intention setting, offer practical ways to harness the power of the mind. Quantum healing explores the mind-body connection and the potential for consciousness to influence physical health. While empirical evidence is still developing, these practices and therapies offer promising avenues for improving mental and physical well-being. 7. Ethical and philosophical considerations. The ethical and philosophical implications of quantum mind theories are significant. Issues related to free will, moral responsibility, and the nature of self are brought into sharp focus by quantum perspectives. The interconnectedness of all things, as revealed by quantum mechanics, underscores the importance of compassion and empathy in ethical decision-making. Philosophical reflections on identity and existence challenge traditional paradigms and offer new insights into the nature of reality. 8. Future directions and research. Looking ahead, the future of quantum mind research holds immense potential. Ongoing studies in quantum consciousness, advancements in technology, and interdisciplinary collaborations are likely to yield new discoveries and breakthroughs. The integration of quantum mechanics with neuroscience and cognitive science promises to deepen our understanding of the mind and its relationship to reality. As research progresses, it will be crucial to address ethical considerations and promote public awareness of these evolving insights. Final thoughts. The transformative potential of understanding the quantum mind is vast and far-reaching. By exploring the intersection of quantum mechanics and consciousness, we open the door to new ways of understanding ourselves and our place in the universe. The insights gained from this exploration challenge traditional views and offer a more nuanced and interconnected perspective on reality. As we continue to investigate the quantum mind, we are encouraged to embrace curiosity and open-mindedness. The quest to understand consciousness and its quantum nature is not only a scientific endeavor, but also a philosophical and existential journey. It invites us to reflect on the nature of reality, the limits of human knowledge, and the profound mysteries of existence. The exploration of the quantum mind is an ongoing and dynamic field, with many questions still unanswered and new discoveries on the horizon. We are at the forefront of a journey that promises to reshape our understanding of consciousness and reality. By embracing further exploration and inquiry, we contribute to a deeper and more holistic understanding of the mind and its place in the universe.